Yes, anybody can tell me what do you mean by harmonic vibration? So, like harmonic vibrations are basically vibration which are of sinusoidal nature, or the applied disturbance is of a sine wave form or a cosine wave. Cosine wave can be reinterpreted in the sine wave form. So, those kind of disturbances are called as harmonic excitation or harmonic source of disturbances. Okay. So, we in first earlier cases we just hello. हाँ नहीं 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 हाँ बोलिए क्या क्या काम है जल्दी बोलिए नहीं नहीं अभी अभी मेरे पास टाइम नहीं है Alright. So earlier we saw examples in which a what do you say, a force is directly applied to the mass, and we saw the effects of that harmonic force on the and how the vibrations are created in a damped condition with a spring attached to it. Alright. Now we will see some more examples. So let's go through the let's go through do a quick recap of the example which we have already studied. So first example or first application which we studied was of rotating imbalance. Okay? So in this case there is a unbalanced mass which is rotating at a radius of e. So when I apply the D'Alembert's principle, it is summation f is equal to m minus m0. So this mass m0 is translating as well as rotating, okay, while the rest of the mass is only translating. So I have subtracted that mass m0 from the whole and I have written the D'Alembert's equation. So it is m minus m0 into x double dot plus m0 into the second derivative of the total displacement, that is this translational plus the rotational. So that gave me the acceleration excuse me, and then I wrote the D'Alembert's equation on the left hand side. I added the damping force and the spring force. So when I rearrange these terms, I get the equation mx double dot plus cx dot plus kx is equal to m0 e omega x square, which is similar to our the equations which we have earlier written. That is f0 mx double dot plus cx dot plus kx is equal to f0 sine omega t. Okay, so equating f0 to m0 e omega square, I get the steady state amplitude. X is equal to f0 by k, that is equal to m0 e omega square divided by k. That k I can rewrite it as m omega n square, and I can take the term m0 e by m on one side, and I can write the equation as x divided by m0 e by m is equal to r square upon square root of 1 minus r square whole square plus 2 zeta r whole square. Okay, so that gives me the equation for steady state amplitude in case of rotating unbalance. Okay, then we saw an example of support excitation. So in this case, the support itself has some what you say, a force applied to it. And that is inducing the vibration. Can you give an example of such case where the support itself is acting as a source of excitation? Okay, can you, before that, can you give an example of rotating imbalance? What would be an example of a rotating imbalance? Yes, anybody? Hello.
So the
How about
dryer
a
washing machine.
Dryer, correct, or dryer of a washing machine. If you see over a period of time, if you have a new machine, the dryer of the washing machine is rotating in a very smoothly in a vertical axis. Over a period of time, there is some wear and tear, and then the dryer starts to wobble a little bit. So that is an example. Or your what do you say, ceiling fan. All right. So some disturbance, some wear and tear of the bearing causes the unbalanced forces, and it doesn't rotate along a vertical axis, or there is more disturbance in the vibrations. So similarly, we saw an example. We discussed support excitation. So in this case, for example, suppose. So can you give an example of support excitation? What do you mean by support excitation? So suppose there is a what is it, a vehicle moving on a road, and the road is not like very smooth, right? And there is a vehicle moving on it. So in this case, the support is like the road, and this sources of vibration are from this unevenness of the road, which are causing vibration. So that is an example of a vibration, force vibration due to support excitation. All right. So just we are seeing some examples, and we are seeing some applications under various scenarios. Okay. So suppose now I can mathematically assume that this is a sinusoidal profile, and I can say that the disturbance is y is equal to y sine omega t. So that is the y is the amplitude of this disturbance. Okay, so that is the harmonic displacement applied to the support. So x is the absolute displacement, and x minus y is the displacement of the spring, that is the relative. Okay, that is the relative displacement, and x dot minus y dot is the velocity of the damper. All right, so I can write this equation summation in D'Alembert's in the form of D'Alembert's principle by writing it as summation f is equal to mx double dot, that is equal to minus k into x minus y minus c into x dot minus y dot is equal to mx double dot. Okay, and I can rearrange these terms and take all the y terms on one side, and I can rewrite it in this format. So this equation I can simplify as sine alpha cos omega t plus cos alpha sine omega t. Okay, where sine alpha is c omega upon square root of k square plus c square omega square, and cos alpha is k divided by k square plus c square omega square. So RHS becomes y square root of k square plus c square omega square sine omega t plus alpha. Okay. So, and which reduces the equation to the format mx double dot plus cx dot plus kx is equal to y into k square plus c square omega square sine omega t plus alpha. Correct? Which is similar to our equation that is f0 mx double dot plus cx dot plus kx is equal to f0 sine omega t plus alpha. All these things were done last lecture. I hope you are able to recall it. Okay, I'm just doing a quick recap. So I can say that f0 is k square plus c square omega square. So x is equal to f0 by k, and again I can write it in the format, and this whole thing simplifies, and numerator becomes 1 x divided by y is equal to 1 plus 2 zeta r whole square divided by 1 minus r square whole square plus 2 zeta r whole square. Okay. Any questions? Okay. Now the only variation here is this: the sign which is taken is of the term omega t plus alpha. Okay. Instead of omega t, it is omega t plus alpha. So there is this additional alpha. So I can rewrite. So when therefore the steady state response is sine omega t minus omega t plus alpha minus phi. Okay, and I can rewrite this as omega t minus phi minus alpha. So the phase lag between the support excitation and steady state response is not phi, is not alpha, it is phi minus alpha. All right. And phase lag is phi minus alpha, where phi is tan inverse of 2 zeta r minus upon 1 minus r square, and alpha is tan inverse c omega by k, that is 2 zeta. Okay, so the phase lag will be this whole term, not just 2 zeta r upon 1 minus r square, which is the case for. So this is for the rotating imbalanced. Okay, so in addition to that, you have to subtract with this another term. Right. Now. So this was in terms of absolute amplitude. Now let's write for relative amplitude. So relative amplitude, I can write relative amplitude is z, that is x minus y. Then I can write that z dot is equal to x dot minus y dot, and z double dot is x double dot minus y double dot. All right. Therefore the equation becomes, I can rewrite this, x double dot is equal to z double dot plus y double dot. Okay. Now the equation for the support excitation is mx double dot plus c x dot minus y dot plus k into x minus y, and this is equal to 0. All right. So let's substitute x double dot is equal to z dot plus y double dot. So I am going to do that. So this is z double dot plus y double dot plus c into z dot, that is from this second term, c into z dot plus k into z is equal to 0. Right? So I can write this as mz double dot plus cz dot plus kz is equal to minus m into y double dot. Right? And so again, so this simplifies to mz double dot plus cz dot plus kz is equal to m omega square y sine omega, right? Which is similar to our mx double dot plus cx dot plus kx is equal to f0 sine omega t. Right? So where our f0 in this case is this term. Right? This is f0. Right? So I can write z is equal to f0 by k again, and divided by square root of 1 minus r square whole square plus 2 zeta r whole square. Okay, where f0 is the coefficient of sine omega t, so that becomes m omega square y divided by k, which reduces to the form of r square upon square root of 1 minus r square whole square plus 2 zeta r whole square. Okay, and if you recall the equation for rotating imbalance, this equation is similar to the rotating imbalance equation. All right. Now, what will be the phase lag for the relative amplitude? So what will be steady state response? So steady state response will be z sine omega t minus pi. Okay, and the phase angle will be tan inverse of 2 zeta r upon 1 minus r. All right. Any questions? So we have constructed this equation in terms of relative amplitude, that is z. Z is the relative amplitude. Now let's compare the equations which we have got for support excitation with the rotational impedance. So for support excitation, in terms of relative amplitude, I get the equation z by y is equal to r square upon square root of 1 minus r square whole square plus 2 zeta r whole square is equal to x divided by m0 e by m. All right, so this is for the rotating imbalance, and this is for the support excitation. Right. So let's see what is the similarity between these two. Support excitation, rotating imbalance. Right. So Z, what is Z? Can somebody tell me? Hello. Can somebody tell me what is Z and what is X?
So Z is relative amplitude. No?
Relative amplitude, correct. It is relative amplitude of relative amplitude at what?
Steady state.
Steady state. Okay, so it is this. So instead of relative amplitude, we should call it. It is a steady state. The relative amplitude. And what is X? And this is for support excitation. And what is X?
Steady state amplitude.
Steady state, but it is an absolute amplitude. Right? It's absolute amplitude for at steady state, or I can say it is a steady state absolute amplitude. Okay? And second point, what is Y here? And what is M0E? Right? So support excitation is what we are assuming, that there is some kind of a sinusoidal profile on that some vehicle is moving. Okay. So what is Y in this case? It is the amplitude of this waviness. All right. So this is the amplitude of that. So it is what? The amplitude of the source of support excitation. So whatever supporting structure or supporting base this vehicle is moving, that is the amplitude of that. So it will be the amplitude of this waviness, which we are mathematically model it to and assumed it to be a sinusoidal wave. Okay. And what is M0E? Yes, anyone?
Rotational imbalance.
This is a rotational imbalance. Okay. It is a rotational imbalance, which is the source of the disturbance, which is inducing the vibrations. Okay. And M is the total mass of the body. It is a total mass. Okay. So I can write X divided by M0E by M is equal to Z by Y is equal to R square upon square root of 1 minus R square whole square plus 2 zeta R whole square. Okay. And I call this term as dimensionless amplitude ratio. Okay. Amplitude density. Okay. So we have studied the characteristics of the harmonic excitation, magnification factor versus frequency ratio. So similarly, we'll study the characteristic curves for both these curves. Why I have clubbed these two together? Because you might be asked to draw the curve and explain the behavior, and this way, if you see both the curves, the nature of behavior of both the curves will be same. So it is easier to remember instead of remembering it separately for each different type of curve. Okay? So this way it is just easy to remember. All right. So let's list out the characteristics, just like we listed the characteristics for magnification factor. So let's see. So when R is equal to 0, what will happen to the value of dA? Yes, can anybody tell me? Hello. Just substitute R is equal to 0 in this. So what do you get? Hello. Yes, this will be equal to 0. All right. So what does that mean? So if I plot a curve of frequency ratio on one side and say dimensionless amplitude or X or Z on one other side. So what will be the curve? What will be the starting point of all the curves? all the curves will start from 0, correct? All the curves will start from 0. Alright, so all the curves, starting point of all curves is this origin. Okay. For an undamped system, so for undamped system, what will be zeta? Hello.
0.
Zeta will be 0. Alright. So this value of dimensionless amplitude becomes plus or minus r square upon 1 minus r square. Okay. So if a system is undamped, okay, and let us consider the case of the resonance. Okay, so where there is resonance. So when at resonance means what is the frequency ratio? Yes. What is the frequency ratio at resonance? Hello.
1.
1. All right. So what happens to this dimensionless amplitude? It goes to infinity. All right. So for an undamped system, these curves will go to infinity. And what happens when r goes to infinity? What happens to this dimensionless amplitude? Can somebody tell me? Yes. Put the limit to this equation as r tends to infinity. So what will be the limiting value? Limit of plus or minus 1 r square upon 1 minus r square as r tends to infinity. So at limit, what will be this value? And limiting conditions of r tends to infinity. So this axis, horizontal axis, is going to infinity. Yes? Anybody? So I can write it in the form 1 upon r square minus 1. Alright, and taking a mod of this because it is plus or minus, so minus sign will come below the axis. So what we take the the reflection of that. So this term at infinity tends to 1, right? So all the curves will tend to 1. Correct? Any questions? All right. So where r tends to infinity, dimensionless amplitude tends to 1. Any questions? So now let's see the peak values. When you get the peak value. So in case of magnification factor also we have derived the peak values. So let's maximize the dimensionless amplitude. So to maximize, what do we do? What should we do? Hello. How do we maximize? Take the derivative of this dimensionless amplitude. Whole square plus 2 zeta r whole square and equate it to 0. So when I take the derivative of this and I simplify, I get these values. R is equal to 1 upon square root of 1 minus 2 zeta square. So what was the max for magnification factor? Can somebody recall? R max corresponding to when we maximize this same term for similar term for magnification factor. Hello. What is the equation for magnification factor? One upon square root of 1 minus r square whole square plus 2 zeta r whole square. Correct? Correct or wrong? Hello.
Yes, sir.
Okay. So what was the maximum value corresponding to the peak values when the magnification factor was maximum? It was r corresponding to mf max was equal to square root of 1 minus 2 zeta square. Okay. So here in this case we get a reciprocal of that. Okay. So when r is equal to 1 upon square root of 1 minus 2 zeta square, the dimensionless amplitude will have peak values, right? Or I can say for peak values 1 minus 2 zeta square should be greater than 0, or 1 or zeta should be less than 1 by root. Right? So in this case you will get the, so when the values of zeta are from 0 to 1 by root 2, you will observe peaks. Okay. What happens when zeta becomes greater than 1 by root 2? Yes? Hello. What will happen to the equation if zeta is greater than 1 by root 2? Yes? Anybody?
So the under root will become negative.
So the this term will become negative, right? So this square root will become a complex number, all right? So when something becomes complex, in that case, what will happen to the peaks? What if you remember the magnification factor curve, the peak starts to disappear, okay? And in this case, in the earlier case, hello, बोलिए बोलिए. कहाँ से? क्यों, किसके लिए? नहीं, all right, so this curve will so our curve is earlier the magnification factor was at infinity, it was going to 0, but here as the frequency ratio tends to 1, our curves tend to 1, right? So so let's plot this using all this. So this becomes complex. So the peaks will disappear, and let's see what happens to the curve. So we'll plot this curve. So we'll plot dimensionless amplitude on y-axis and frequency ratio on x-axis. And we have derived some very useful results. On around this coordinates, we have to balance this curve. Okay. So one is this when this dimensional amplitude is 1, and that is the important point. And second is the point where resonance occurs. That is where r is equal to 1. Okay, and this r is going to infinity over here. All right. So let's start with the most critical curve. That is the when zeta is equal to 0. So when zeta is equal to 0, this dimensionless amplitude goes to infinity at resonance. Okay, and then this curve will come down and will die out at dA equal to 1. Right? And as long as zeta is greater than 1 by root 2, you will observe peaks. All right. So here in earlier case, if you remember the magnification factor curve, the curve, what was the, how were the peaks shifting? R corresponding to dA max is equal to 1 upon square root of 1 minus 2 zeta square, correct? Alright. So as zeta increases, if you remember the magnification factor peaks, they shifted to left. Alright. So can you tell me what will happen to these peaks when zeta increases? So you will get a peak. So suppose zeta is equal to 0.1. Can you find out what is the peak value? R corresponding to what is the dA max? R max value for zeta equal to 1. Can somebody find out? Let's say zeta is equal to 0.25. Just substitute zeta is equal to 0.25 in this and tell me the value of R. Table zeta and R. So first value is 0.25, second value is 0.5. Tell me the values of R. Hello, is anybody calculating? Hello, is anybody calculating? All right. So as you can see, this value will go on increasing for as you increase this zeta, and this curves will shift to the right. Right? And when zeta goes to beyond root 2, when zeta is greater than root, so this is for zeta less than root 2. When zeta is greater than root 2, then this curves will disappear and this will monotonically increase to 1. Right? Curve. So all these are for zeta less than 1 by root 2. Then this is the critical curve where zeta is equal to 1 by root 2 and zeta greater than root 2. You can see that the peaks are disappearing. Any questions?
No.
All right. So to summarize, when zeta is less than root 2, R is greater than 1 and peaks occur to the right of the resonance. So for zeta, for values of zeta between 0 and 1 by root 2, as zeta increases, R increases. Okay? And the peak shifts to the right. For zeta greater than 1 by root 2, the values of R will become complex and dimensionless amplitude monotonically increases without any peak value. Okay. Okay. So let's do one example. A motor vehicle can vibrate in a vertical direction while traveling on a rough road. The vehicle has a mass of 1200 kgs. The suspension system has a spring constant of 400 kilonewton per meter and damping ratio of 0.5. If the vehicle speed is 20 kilometers per hour, determine the displacement amplitude of the vehicle, and the road surface varies sinusoidally with the amplitude of y equal to 0.05 meter and wavelength is equal to 6 meters. All right. So let's solve this example. So here you have a road. This road is of a sine wave format. This is 0.05 meters. Wavelength is 6 meters. Okay. So V is the velocity of the vehicle is F into lambda. And V is 20. So that is the frequency of the F is the frequency of the support excitation. That is kmph. So that is 20 into 5 by 18 meters per second. So substitute that and find out the value of F. Lambda is 6 and tell me the answer.
Zero 0.9267.
So that is in hertz, so convert that into radians per second. So whatever value you get, it is omega is twice pi into F. So convert into radians per second and tell me the value.
.582.
5.82 radians per second. So this is what? This is the forcing frequency. Alright, so this is the forcing frequency of this support excitation. Alright, so the frequency ratio R is equal to omega by omega n, and omega n is square root of k by m. Substitute the value of k and m in the equation and find out omega n. And tell me the value of R. This is the frequency ratio. Are you calculating?
Sir, omega n 18.26.
18.257 radians per second, and R is omega by omega
0.318.
0.3186. 3186. That is the frequency ratio. Now what is asked in the question? You have to find the amplitude of the vehicle. Okay, so you use the equation x by y is equal to square root of 1 plus 2 zeta r whole square, okay, upon square root of 1 minus r square whole square plus 2 zeta r whole square. So y you already know. What is y? It is given in the question.
0.
0.05 meters. Okay, and what is zeta? Damping ratio
0.5.
0.5. Okay, so substitute those values in this equation and find out the value of x.
0.055.
Right. So answer is 0.0. Okay. All right. Okay. Next we'll so this is all about the rotating and reciprocating imbalance and support excitation. So one more example we'll see, that is a force vibration due to reciprocating imbalance. So like that is in IC engine. So this is a typical IC engine. So M is the total mass of the engine, and M0 is the reciprocating mass, that is the mass of the piston. Okay. L is the connecting rod, and E is the crank, and N is the obliquity ratio, and omega is the angular velocity of the crank radius in radians per second. Okay. So if I want to write the inertia force acting on the piston, that is equal to MA, that is equal to M into X double dot. So here M will be nothing but the mass of the piston. So it is M0 omega square E. So we are not going to derive this equation. This you have already learned in I think kinematics of machinery. Okay. And that is sine 2 omega t by N, where N is the obliquity ratio, that is L by is called as the obliquity ratio. All right. So this term is very small. Okay. The numerator is very small and the obliquity ratio is very large. So for mathematical purposes, we neglect this second term. Okay. This is almost tending to 0. So inertia force becomes M0 omega square E sine omega t. Right? Sine omega t. Right? And which is similar to our form F is equal to F0 sine omega t. Right? So X, that is the steady state amplitude, I can write it as F0 by K divided by square root of 1 minus R square whole square plus 2 zeta R whole square. Right? And substitute this values. F0 is equal to M0 omega square E divided by K is M omega N square, and divided by square root of 1 minus R square whole square plus 2 zeta R whole square. Right? And taking M0 E by M on one side, and omega by omega N square is R square. So I can write this equation as X divided by M0 E by M is equal to R square upon square root of 1 minus R square whole square plus 2 zeta R whole square. Right? So these are the various 3 applications that you will be studying, and there are many more applications, but numericals will be asked on these 3 applications. Okay. All right. So now you have done so many numericals. So which method to apply? So we'll do one common example, and maybe you can tell me how to select which appropriate method. Okay. So a 82 kg machine tools is mounted on an elastic foundation, and an experiment is run to determine the stiffness and damping properties of the foundation. When tool is excited with a harmonic force of magnitude 800 Newton at variety of frequencies, the maximum steady state amplitude obtained is 4.1 mm at a frequency of 40 Hz. Estimate the stiffness and damping ratio of the foundation. All right. So here the mass is. So let's summarize the data. Mass is 82 kgs. F0 is 8000 Newton. Stiffness is, you have to find out. Zeta is 1. Peak amplitude is given as 4.1 into 10 raised to minus 3 meter. peak frequency is twice pi into fp. So that is twice pi into 40. That is 251.33 radians per second. Right. So let's calculate the stiffness and the damping ratio. So xp by x0 is, so we have maximized this term, if you recall, is 1 upon twice zeta upon square root of 1 minus zeta square. Right? So xp is 4.1 into 10 raised to minus 3 and f0 is 8000 by k is equal to 1 upon 2 zeta upon square root of 1 minus zeta square. And I can simplify this and write everything in terms of k. So tell me what is k? Also, peak frequency ratio is 1 minus 2 zeta square. Are you calculating? So this will be something zeta upon 1 minus zeta square. Tell me the value of the numerator here. Are you calculating? Hello?
Sir,
Yes. Tell me the value. So everybody is aware of the extra. We are losing a lot of practicals. Last week also we lost one practical, and next week also we are going to lose quite a few practical. In fact, both the batches are going to lose the practical because I think Tuesday is holiday, and after that you have your term test. Okay. So I wanted to conduct one practical on MATLAB Simulink. So that is scheduled on Monday 8 to 9. Okay. 8 to 9 a.m. Has everybody received the message? Have you installed MATLAB?
yes.
Hello?
Yes.
Because the MATLAB is, I think most of you might have installed is the trial version. So that is only valid for 30 days. So I wanted to make sure that we finish off that MATLAB part before 30 days. Otherwise, after 30 days, after trial expires, then it will be a problematic situation. Yes, what is the value of the numerator? All of you are aware of this practical, no? It is for the entire class. Huh? So we will be simulating the force vibration system using MATLAB Simulink. MATLAB. Alright, is anybody calculating? Or should I give the value? Okay, so you get one value of k over here. Okay, then I will get another k value from this equation, that is the peak frequency ratio. So Rp is square root of 1 minus 2 zeta square. That is the equation. Or omega p by omega n is square root of 1 minus 2 zeta square, and omega p is the peak frequency that you have already calculated, that is 251.33 divided by omega n is square root of k by m, that is k by 82. Okay. And so this is equal to square root of 1 minus 2 zeta square. So you get another equation in terms of k. So k is equal to something else divided by square root of 1 minus 2 zeta square. So you get two equations of k, one over here, one over here. Equate these two and find out the value of zeta. Is anybody calculating the for the first one? K is equal to This comes out to be 975.61 into 10 raised to 3, and this is 518 into 10 raised to 6, divided square root of 1 minus 2 theta. So equate these two values and find out the value of zeta. Alright, so this is the equation after simplification, or this is what you get. All that, so that will give you two values of zeta. It's equal to 0.984 and zeta is equal to 0.179. So which value will you take? Yes, anybody? So we'll take the value which is greater than 0.707, right? Because that's where we get the peak. So we take this value and this value is neglected. So corresponding to this, k is equal to 5.54 into 10 raised to 6. We end the lecture. So there is a quiz that you have to solve. It is a big quiz. Just click on the link and just see if you are able to open it. Are you able to access it? Hello.
Yes, sir, we are able to access.
Okay, so the first two questions are there on the screen. Okay, so take a snapshot of that. So there are total 25 questions. Remaining questions are also one by one. I will show it on the screen. So all of you take a snapshot of it and you can distribute it in the group and solve it and submit it. So whatever has been covered till today, all those things will be there for your term test too. So if you are able to answer these questions correctly, that means
So will the term test be based on an assignment or will it be a proper online exam?
hello.
Sir, I just
Yeah.
wanted to ask whether the term test will be an assignment or will it be a proper online exam?
I think it will be online exam. Let's unless there is a last minute change. So if there is a change, then we will let you know.
Okay, sir. Because the timetable hasn't been
Timetable has been.
the timetable hasn't yet come, so that is why.
Timetable hasn't yet. So I think I don't know. The decision has not yet been finalized. It seems. So hopefully by Monday or today evening, we will let. We will finalize. All right, that's all for today.